Polymer electrolyte membrane fuel cells currently provide a highly promising, completely zero-emission powertrain for our lightweight, sustainable transportation systems. This Sankey diagram exposes a limitation. We put 100% energy in, but half is lost as waste heat. The challenge is exhaust quality. It strictly sits in the 40 to 60 degrees Celsius range, too low for conventional recovery. To reclaim this energy, researchers are testing an integrated loop, capturing this low-grade exhaust to drive secondary thermoelectric generators and preheat incoming fuel. If this dual recovery mechanism works, it would significantly improve the fuel economy and commercial viability of hydrogen powertrains. Managing this heat dissipation is a critical step in making hydrogen fuel cells a competitive alternative for high-efficiency transportation. A 2026 PhD thesis from University Technology Mara evaluated exactly this kind of integrated heat recovery architecture. Researchers executed this three-phase framework. Phase 1 established the foundation using steady-state computational fluid dynamics. Phase 2 validated a physical prototype inside a controlled lab. Finally, Phase 3 applied the ultimate reality check, dynamic on-road evaluation mounted on a 2-kilowatt buggy. Moving the system from a sterile lab bench to the outdoor driving circuit at UKM introduced a range of chaotic variables that mathematical models often exclude. This transition reveals that mathematical models often overpredict performance because they assume perfect boundary conditions. Trusting idealized, steady-state assumptions without dynamic physical validation creates a technical gap between predicted efficiency and real-world performance. The system's primary success is mapped on this kinetic graph. The initial peak is activation polarization. The energy barrier molecules must cross. When cold hydrogen enters, it acts as a thermal sink, driving the energy barrier up and lowering the final output voltage. The recovery loop mitigates this by routing the 60-degree waste heat into the incoming hydrogen gas stream before it hits the catalyst. This preheating lowers the activation barrier, allowing the fuel cell to sustain higher operational voltages and directly improving efficiency. In the researchers' empirical testing, this thermodynamic trick worked, boosting overall efficiency by roughly 5%. That electrical improvement translated into measurable fuel conservation, reducing hydrogen consumption from 5.2 grams per kilometer down to 4.4 grams. Repurposing exhaust heat to condition reactants is a viable strategy for improving the fuel economy. However, as the physical buggy accelerates, the exposed chassis is continuously subjected to chaotic and turbulent aerodynamic wind. This creates a significant discrepancy between the heat routing in the model and the actual thermodynamic behavior on the road. Thermal mapping revealed a 50% real-world aerodynamics can dismantle steady-state predictions, rendering theoretical calculations ineffective for dynamic applications. Beyond the insulation failures, the study exposed a more rigid limitation. Total waste heat utilization remained strictly bounded below 3%. This low utilization is a result of thermal saturation occurring within the internal geometry of the heat exchanger. A 2-kilowatt fuel cell architecture inherently operates with a very low mass flow rate. This creates a restricted thermal absorption capacity. There simply isn't enough hydrogen mass to absorb the volume of waste heat being produced. This is a fundamental limit of fluid dynamics that cannot be bypassed with better geometric design. Once the hydrogen gas reaches saturation, the remaining 97% of the exhaust heat simply bypasses the recovery system and is lost. An integrated system's efficiency ceiling is dictated not by the total waste produced, but by the physical absorption capacity of the working fluid. Passive heat recovery is a viable strategy, but it is limited by the thermodynamic constraints of low-temperature conversion. This comparison highlights the gap between steady-state predictions and the jagged, fluctuating reality of on-road operation. Contact resistance, thermal lag, and natural convection are dominant forces in physical engineering that cannot be relegated to the margin of a model. Experimental uncertainties and sensor noise are permanent features of any outdoor mobile environment. Researchers must use this volatile, real-world data to continuously correct and calibrate their mathematical models. Improving these systems requires researchers to move beyond the digital vacuum and account for the specific